now have nothing to do on the weekend. Homework 2 is coming out soon. It's due 2 weeks from today. It'll be posted by tomorrow. It's due in 2 weeks primarily so we have a chance to grade it and return it before the first midterm, which is in the middle of October sometime. Today's topic is longest common substring. It's probably the last of the dynamic programming problems that you might have seen before. So if this class is just all too easy for you so far, don't worry. It's going to get fixed. Are there any administrative type questions? Fantastic. So yes. So the homework requires that you have a proof of different things, like you have a proof of the correctness and a derivation of the runtime. I don't mandate a particular form for the correctness proof. Okay, so today's problem is longest common subsequence. So it's an example of dynamic programming. I'll define the problem, then I'll give you a little story about where the term dynamic programming comes from and when it was invented, and then we'll go back and solve the problem. So the idea of longest common subsequence says, suppose I have 2 strings of letters, and I want to know what string of letters appears in order in the first string and in order in the second string, although maybe some elements of the first and second string are skipped. So that's the idea of the longest common substring, and we can do this as an example. We can say maybe I have the substring abracadabra. And I have the substring yabba dabba doo. So these are my 2 substrings, or these are my 2 strings. And what I want is a substring that's a substring of both of these. So what do I mean by a substring? Well, if I just think of the first string, I can define a bunch of substrings. So abra is a substring. That's a continuous prefix. It's at the very beginning of the string, and it's continuous. But another thing that's a substring of that first string is A. That's a substring of the first string because there's 5 A's in the first string. And I could have like what's a good example? BCDR is also one. BCDR. So I like this string because this is something that's a substring. It's in order in the first thing. There's a B that comes before a C that comes before a D that comes before an R. If I try to go backwards, R, D, C, B, that is not a substring of this first string because I can get to the R and then there's a D, but once I get to like the first D after the first R, there's no more C after that, so this is not a substring. So a substring is anything that you can build by going through and saying, here's the first letter, do you want it or not? Here's the second letter, do you want it or not? Here's the third letter, do you want it or not? You can have the empty string as a substring, you can have the whole thing as a substring, but you can't necessarily rearrange the letters. You might be able to have some rearrangements of the letters if those letters appeared in that order otherwise. So the longest common substring says, I want to find a string that is both a substring of this string and a substring of this string. Is everybody happy with that? What's the worst possible way to do this? So I could imagine every substring of this first one, and then I could check every substring of this and see if it's a substring of this. Why is that the worst possible method? There's a lot of substrings. How many substrings are there? Is that right? The power set. That's not a number. 2 to the n. So the number of substrings of this string is 2 to the n, or is about 2 to the n. I guess if you have a lot of the same letter, There might be fewer, but you could build this by saying, do I want this letter or not? 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 This letter, and so there's n characters and 2 choices for each character, so there's something like 2 to the n possible substrings. So if I was to enumerate all of them and then check, that would take a really long time. Who's happy about this? Question?
Wikipedia calls this a subsequence rather than a substring. There's some kind of convention on naming this problem.
Long-term subsequence. I've always heard this called substring. I've heard subsequence too. I don't know the difference. I guess we can. For the purpose of this lecture, this is what I mean by substring. We'll edit the Wikipedia article later. Yes. I like it. Okay, so what is a long common substring for this? Well, you might go through and say, all right, like A, Y, like, so this obviously I can't have A and Y. I have to pick one of these or skip both of them. It seems like there's a lot of A's everywhere and not that many Y's. So let's pick A as maybe the first thing in our output. We might sort of mentally say, hey, these 2 A's are both there. Let's make those match. These 2 B's are both there. Let's make those match. These 2 A's are both there. See, there's a lot of A's in common here. A. Maybe if I do this A, that's not so good. Instead, I could do like, oh, that is pretty good, isn't it? Okay, A, like maybe I could do this D instead. I'm not sure. I get this?
B-I.
The B's, good, okay. And then an A. So maybe that's the longest substring. That's as long as one I found before. So the long substring here is A, B, A, B, A. So that is a six character substring or subsequence. That's a subsequence of both of these strings. Who's happy? All right. So we're gonna. Well, we thought about a really naive way of doing it, which is enumerate all strings. We can now try to imagine a slightly better heuristic way, like maybe there's a greedy algorithm. So when there's a greedy algorithm, you might say, okay, I have these 2 characters, an A or a Y. Like, do I want to, like, obviously I can't use the Y, but if I just see this, if I'm just making a greedy choice that doesn't look at the rest of the string, I wouldn't know if I should like skip the A or skip the Y. So you might say, let's take whichever letter in one row comes up first in the other row. You might have some kind of heuristic like that. Turns out that none of those heuristics work very well. This doesn't admit a greedy solution. So I'm going to try something called a dynamic programming solution. Dynamic programming has this interesting history. It was invented, or the idea was listed in 1952 by an Air Force researcher named Richard Bellman. And he has a great story of how he invented the name dynamic programming. So here it is. He writes from his autobiography. The 1950s were not good years for mathematical research. We had an interesting gentleman in Washington named Wilson. He was Secretary of Defense, and he had a pathological fear and hatred of the word research. I'm not using the term lightly, I'm using it precisely. His face would suffuse, he would turn red, and he would get violent if people used the word research in his presence. You can imagine how he felt about the term mathematical programming. That's what I was working on, but I needed a new name. I felt I had to do something to shield the Air Force from Wilson because I was doing research with the Air Force. What title, what name could I choose? So I ended up choosing dynamic programming because it didn't sound like research or mathematical programming. It sounded good, dynamic, crazy. These are the games people play to get fun. Awesome. Okay. Brute force search. So if we want to do a dynamic program, then what we need is to think about sub-problems. We need to say, I have 2 long strings. I want to break the question of what is the longest substring common to both of these into a simple thing I can answer right now, maybe with some choices. Maybe I don't know which one is best. But I want to have a recursive formulation that says, okay, you're trying to do a big, long substring. Here are some choices you can make. And here are some sub-problems that relate to the rest of this. So, who wants to throw out suggestions of how I could say I have string X, let's call this string X, and string Y, and I'm trying to build a string Z, but really what I want to know is how long is the best string Z. And I'll give us a little bit of terminology here. So I'm going to say the longest common substring of X and Y, which goes from 1 up to M. Where's Y? 1 up to M, and Y is 1 to N. So I'm trying to find the longest common substring of these two strings. All right, so I could return the answer 3, because probably there's about a 3-element substring. That may not be the right solution. I want to express this in terms of smaller subproblems. And I want somebody to throw out an answer, and I'm happiest if that answer is wrong. Yes?
Could you summarize by maybe counting the problem? You know, it would be more than the multiplier
I know it's not going to be more than the number of characters, whichever one is smaller. Is that what you said?
The number of characters are you will strings whatever you will bound the problem.
Oh, I see. So you're saying, I'm not sure if you're saying if this string is really long and I have to do like the 2 to the n, like the 2 to the n search, I could be like, well, let's just do 2 to the size of the shorter string and make my life easier. Okay, that's a good idea, but it still has that exponential thing, and your evil adversary is going to make both strings the same, so that doesn't help you that much. All right, do you have a wrong answer?
I have a clarification. I think what you were saying is if a letter does not actually occur at all in both strings, so you can do that.
I see.
And I also have another answer, which is probably the right answer.
Let's stop with the first one. So this is
I have the wrong answer. Cast the magic spell and randomly select, and hope the random number generator selects the right substring.
That's even worse than the brute force. Okay, so one thing is to say, we might be able to make life faster if we say, like we can look through in, I guess, order n time. We can look through what all the letters are, and for each letter, we can say, does that letter ever appear in the other substring? So if we have this like Y that never appears, we could be like, hey, the Y never appears. Just chuck it. And so in a small amount of time, maybe we can make these strings shorter. In this case, I guess this would get rid of the Y and the O's, but everything else appears in both cases. Sorry? And the R doesn't appear on the bottom. Okay, cool.
Are we allowing like skips?
You're allowing skips. Like this AAB skips many letters in each.
Well, so that might actually.
So throwing out letters might be good. It might be bad because you're losing. Well, a letter that appears in one and not in the other can't possibly be in a common substring. So I think that's safe to throw out. Okay, so if something appears in one and not in the other, we can throw it out. Sure, I like that. What else? Are there any other tricks we could use like that? I don't think these end up being good for the final solution, but I like hearing tricks. Yeah.
The longest common substring in the shorter one of those, a portion of both of those strings, by also be the longest possible substring in the full string. Like that might.
So the longest common substring in a short portion of both strings might be part of the longest common substring in all of it.
Yeah.
So if you were to say, let's take the problem and chop it off somewhere, like here, and if I found the longest possible substring of these, maybe that's the longest possible substring, plus like maybe I can separate the problem in two pieces like that. That's correct. We're going to have a refinement because we might have to chop it here, but maybe the longest common substring matches some things from here up to some things from here. So you have to think carefully about how we chop things up. One other heuristic, going back to the idea of like if there's no characters in the other one, suppose you have a character that appears just once in each string. So suppose there was a Y. Suppose there was in some long string that I'm not going to tell you what it is. Like suppose there's like a Y here and a Y here. And that's the only time Y appears. Then you might be able to say, I have two subproblems. Either this Y matches this Y, and I have both this longest common substring and this longest common substring, case one, or this Y doesn't match in the best solution, and I take it out and then compute the longest common subsequence of these two strings without the Y. I guess if you had a single occurrence of Y in one string and multiple occurrences of Y in the other, you could be like, well, maybe this is a match, and I get these two subproblems. Or this is the match, and I get this as a subproblem, and this as a subproblem. Or I take it out entirely. Maybe if there's just two Y's in one string, like I have a Y and some number of Y's in the other string, like more than two, because that's the case. I could imagine all K choose two ways of signing these Y's to these Y's and get a bunch of, but now I'm starting to get polynomially many subproblems that I'm generating, and my algorithm is getting more complicated, meaning it's less likely I'll program it correctly. So these are all sort of interesting ways we could say I have substrings, and I want to break my big substring question up into smaller ones. But maybe we can have that smaller subproblem be even easier to define. So the idea of this, or the substructure that we're going to look for, is based on prefixes. So we're going to build the longest common subsequence, the longest common substring, based on prefixes of these strings. So we're going to imagine that in our recursive call, we're going to say this is asking about the entire string X and the entire string Y, and we might call this recursively on things like X from 1 up to M minus 1. So everything but the last character. Or Y, everything but the last character. And so that's going to be our way of solving this problem. So when you think about the longest common substring of these strings X and Y, what we're going to think about is all possible subproblems where I use the first some number of characters of X and the first maybe some other number of characters of Y. And so in our recursive call, we're going to imagine subproblems of this form. What subproblems does this not include in our final solution? We're not going to imagine a subproblem that is like some interior part of the string. We're just going to use the prefix string. So here then is our recursive formulation. The longest common substring of I to J. And I'm going to say this as shorthand for A from 1 up to I and string B of 1 up to J. But if I had that longest common substring with these brackets and so on, life gets just hard to write all that stuff down. We're always going to start from the beginning of the strings. And so if we're going to go for a string A from 1 to I and B to 1 to J, then we're sort of thinking about, I have this problem and I can go to shorter prefixes. So I'm going to think about the last two characters and can I get rid of them? So what's the idea? If I have two strings and the last character is different, then if this character is different, then it's not the case that I know right now what character should be in my substring. What I know is that these are different, so that's obviously not the right match. So maybe my longest common substring is the longest common substring of these two strings, or maybe it's the longest common substring of these two strings. All right, so we can say if AI is not equal to BJ, then I want to return the max of the longest common substring of I comma j minus 1 and the longest common substring of I minus 1 comma j. Otherwise, suppose we're in a world where these last two characters do match. So I'm going to change the problem now. The last two characters do match. Then the longest common substring of these two strings could have an A at the end of it. In fact, I'm going to prove in a second it must have an A at the end of it. And so the longest common substring of these two strings as they're written is going to be 1 plus the longest common substring of everything before them. So we can return 1 plus the longest common substring of I minus 1 comma j minus 1. Who's happy with this? Who's never been in one of my classes before? Everybody's been in one of my classes before? Raise your hand if you've never been in one of my classes before. Before this semester, yes. I grant, that's a different question. So I picked up this nervous tick. It's not really nervous now, I just do it out of charm and history, but during my PhD defense, one of the faculty asked me a question, and I answered it, and it was like a long, convoluted answer, and I said, "Are you happy?" And he said, "Robert, my happiness is completely unrelated to your answers to my question." Okay, so now I go back to So here is our recursive algorithm. The beauty of recursion is that this algorithm is done. So how long will this algorithm take? There's actually an easy answer for all these things. How long does the algorithm take on an input of size n? Or like n comma m? It's going to be t of n comma m. That's always the answer. How long does it take? T of n comma m. All right, now what is t of n comma m? Well, that equals, in case 1, we shorten one of the strings, and we have to compute this as a recursive call. So it's t of n minus 1 comma m plus t of n comma m minus 1. And that looks kind of ugly because I'm not making these numbers go down very quickly, and I have 2 subproblems, and life's going to become miserable really quickly. So if I just do this as a recursive formulation, this ends up being exponential time. It has this property that dynamic programming problems have, that even though we have this recursion and it looks horrible, there's overlapping subproblems. I don't have to go very far down the recursive tree to end up with exactly the same subproblem. So in particular, if I go down this recursive tree, I do the longest common subsequence of I comma j minus 1. So I'm here at I comma j. I have my 2 recursive calls. I have I comma j minus 1 and j comma I minus 1. The next time, I'm going to have 2 more recursive calls, I comma j minus 2 and I minus 1 comma j minus 1. And here I have the solution I minus 1 comma j minus 1. I'm going to have bad notation here. I didn't have the same order. Okay, so even here, these are the same subproblems. I minus 1 comma j minus 1. So that's why this recursive tree does not explode if you are careful about it. And so we could add a memoized version of the longest common subsequence, which is what we talked about last time, which says, as we write this routine, you have a little check that says, have I checked I comma j before? If I have, look up the answer and return it, and cut off that recursive tree. And if I haven't, then do this, and then write into my memoized answer that recursive call. All right, so that's the run. So if we have that, if we imagine this memoized version, so if memo I comma j exists, return it. I've always wanted there to be a programming language that understood prepositions like return it. That'd be awesome if a compiler could be like, return it. Give me the answer I want. And otherwise, this is sort of a big else loop. Else do all of this. And then instead of return, we also like save answer into, save it into memo of I comma j. So how much time does this take if we have the memoized version? Well, if we have already computed something, it takes order 1 time to return it. It's constant time to return it. If we haven't, then the call where we compute something for the first time is going to generate 1 call. Actually, it's going to generate 2 calls. In the worst case, it generates 2 calls. Otherwise, it just generates 1 call. So it generates 2 calls. So that's a constant time. It generates those calls, but we can figure out how much time they take once we're talking about that call. But the I comma j call is either constant time or it generates 2 calls, but it's constant time. So everything is constant time in this loop. And the only question is how many different I comma j combinations are there? So how many different I comma j combinations could there be? M times n. If there's a string of m and a string of n, there's m times n. So that's going to be the total runtime of this algorithm. So the last part of this is we need to prove that it's correct. And so what does the proof of correctness need to show? It needs to show the following. It needs to show the following. So we need to say the longest common substring of I comma j really is 1 plus the longest common substring of I minus 1 comma j minus 1. If these two are the same. And if these two are not the same, we need to say the longest common substring of I comma j is either this one or this one. Is everybody happy with that? All right, and the other part of the proof, in this case, is really easy. It says we need to have this optimal substructure property that says not only is this the right answer, but I have a valid solution. So when I use this character, AI or BJ, if they're the same, when I use that character, that doesn't somehow foul up the rest of the longest common substring. That seems really obvious, maybe, that if I use this last character, like if I use this last character in my optimal substring, then the rest of the optimal substring isn't affected by anything. But you can imagine a problem that says, longest common fair substring. If you said, if I use a character, I'm only allowed to use it in my longest common substring twice. This is a different problem, but it doesn't feel that different. I say I have 2 strings, I want the longest common substring, and you're not allowed to use any letter more than twice in your answer, in your common substring answer. If I did that, then what this letter was here, this letter A, what that letter choice was, would affect what choices you could have in the rest of the subproblem, right? So that's a case where what this letter is affects things. We don't have that in our problem. We're just trying to find any long common substring. So then this longest common substring of the shorter strings is the same problem. It's the same optimal problem. So let's write out that proof formally. So we say, let's do case 1. Suppose xi equals yj. So suppose I'm in this I have changed my variable name. AI equals bj. So if that's the case, then suppose AI equals bj. If that's the case, AI equals bj. AI equals bj. Suppose AI equals bj. So then I want to argue that the longest common substring I comma j equals 1 plus the longest common substring of I minus 1 comma j minus 1. So we know that we get this one character for free. So the question is, and it seems like a dumb question a little bit, but it says, like, is there something better that could happen? Is there some better way to solve this problem? So if we have our optimal solution, that uses this final character. So we have a solution that uses this character. Is there some better solution that doesn't use this character? That's the answer that we're trying to. The answer is no. And the argument could be, suppose optimal solution doesn't use AI, which equals BJ, as its final character. Suppose the optimal solution doesn't use AI as its final character. All right, then the optimal solution so maybe we want to say, without loss of generality, suppose, like, define the size of the optimal solution as k. All right, so we say, without loss of generality, let the optimal solution size be k. I'm just giving it a number. The optimal solution has some size. I'm just giving it a variable so I can talk about that. Now we say, suppose that optimal solution doesn't use AI as its final character. Then the optimal solution for LCS of I minus I comma j, I comma j, equals the longest common subsequence of I minus 1 comma j minus 1. Because I'm not using that final character, so I might as well chop it off both strings. So then, the LCS of I minus 1 comma j minus 1 equals k, because it's optimal. And I can make a new optimal solution opt star as the LCS of I minus 1 comma j minus 1 plus my last character a sub I to get solution of length k plus 1, which is longer than the optimal solution. Which is a contradiction. Okay, so all of this says, if I have my longest common substring and the final two characters match, I should take that final character and put it in my substring, and I should count the score of how long this substring could be as 1 plus the longest common substring of the two strings with the last character taken out. Why do I say that? I say, suppose the optimal solution has size k. I'm just giving it a name. And suppose that optimal solution doesn't use that last character because it's so clever it doesn't need to, or something. I don't know how the optimal solution wouldn't use that. But suppose that happened, then if the optimal solution is size k and it doesn't use this letter, this last letter, then it must be the optimal solution to some set of characters that don't use that last letter. So if that optimal solution has size k, I could make the optimal solution better by adding this last letter a. And that's a contradiction because I can't make the optimal solution better. I drew it, I magically said, let's imagine this optimal solution, grab a handle onto it, and then talk about its properties. Yes?
I think I would BJ.
You can still use BJ. So these, like, AI equals BJ.
Yeah.
So these are the same things. Like, this is, maybe I don't understand your question.
LCS IK equals LCS IK minus 1k.
You're saying the optimal solution could, see. Yeah.
It doesn't matter, so you can switch.
It doesn't matter because you can switch.
to the small plus optimal.
But the other thing is, why would you, like, why not use the last one, right? Like, if, so you're saying this, I see, the opt star could be, why could it use BJ? So you're like, the idea would be that like your last letter could be tied into something else here.
Yeah. So you have to, we use the bottom level of B or.
If you use the last letter of B or not.
So like if you put an extra A on the end of X, like abracadabra, like if you put another A on there, then you could not use the last letter of X without hurting your optimal solution, but you could switch into the optimal solution strategy without making your solution any worse every time.
Right.
Right. Right.
Just that it's not worse. So how do we have, so what do I have to change in my proof to address this?
So where you say that the opt solution for LCS ij equals LCS I minus 1 j minus 1, then that's not, you can't necessarily say j minus 1.
So this goes to j?
Well, so it basically either the last letter of bj gets matched to something else and you did just as well. Like the proof is essentially correct. Like there's not a major hole in it, but it works.
But this part, like this part fails then, right? Because I can't construct the opt star unless I have, that is too big unless I have this extra character. So you're saying the opt has to be the max of those two? But I don't like that because I can't add a character unless I've shrunk both of them, right?
It's more like that sometimes you can do as well as the optimal solution without using both last characters.
Right.
But that's okay.
But you can never, the
optimal solution is always at least as good. It's either better or equal to the other strategy.
So how would so I can use this to get a solution of k plus 1. Or, so what's the, or?
So, or, like, or a bj is matched to another letter still, like already. So you can't add the plus 1 because it's already that length.
Oh, I see. So you're saying opt star equals this, or opt star just equals, like, or I can't add anything.
Right, because it's already.
Or opt star equals LCS of I, comma j minus 1 max, or LCS of j minus 1 comma I, maybe. Which is not longer than we've gone off the rails. Yeah. We've gone dramatically off the rails somehow. All right.
Your proof is essentially correct, so I think just post about it later. Like it's true. Right? Like.
So proof is confusing, isn't it? Like correct, right? Like a proof is supposed to be an explanation that convinces somebody. So like if it's gone off the rails, that's bad.
Well, if it doesn't use AI or BJ, then taking off both of those won't affect the solution. But if it uses one of them, then taking off both characters actually shrinks the solution by 1. So adding text back on would arrive at the same contradiction.
Okay, so let's go through those cases. So
Yeah.
the optimal solution either uses, okay, here we go, let's try this. Uses AI and BJ, like as a combination, and then it's the same as our solution. And we're done. Or it uses neither AI nor BJ, and then our argument here follows.
Mm-hmm.
Or opt solution uses AI but not BJ. Okay, so what happens if our optimal solution uses one of these two letters that are identical at the end, but not the other one? So that means our optimal solution goes through, and let's say it uses this A, but not this A. So if it uses this A but not this A, then because maybe it's going back to here, maybe that's what the optimal solution is thinking, then the size of that optimal solution is the size of the optimal solution for my string that doesn't include this last letter. But there's nothing left for this letter to be matched to. So the size of that optimal solution has to be the size of, so if I'm using I but not BJ, then it's the same size of an opt. No, opt is the size of the longest common subsequence. And so here's the argument. So the opt size is going to be, so my longest common subsequence from I to J is going to equal, I'm matching this letter to something earlier. So it's going to be, I'm matching this letter to something earlier, but earlier than it needs to, so that's kind of foolish. So it's going to be the longest common substring where of okay, so if I use this last here's the argument. If I use this last letter, I could match it to this last letter, and my answer would be 1. Here's a new argument. 1 plus the longest common substring of I, comma I minus 1, comma J minus 1. If opt is even more foolish and matches this letter to something earlier, then opt solution is going to be 1 because I got this last letter. 1 plus the longest common substring of I minus something bigger than 1 because I'm going further back on the okay. I minus something big. What letter connotes bigness? B. We are using B. H for huge. I minus something huge, comma J minus 1. So if we use both of the last letters, if opt uses both of the last letters, then this is the size of opt. If opt doesn't use both of the last letters, it uses 1 and then matches that to something earlier in the previous string, then this is the size of opt. And the longest common substrings can only get bigger if you're like using a longer prefix. Okay, so let's try to rewrite that so that I don't have random stuff on the board. Okay, so if opt uses AI but not BJ, then the optimal size of this longest common substring of I, comma J equals 1 plus the longest common substring of I minus H, comma J minus 1, where H is bigger than 1 because opt made a dumb decision and didn't use the last one. And this, because the longest common substrings are operating on prefixes, if I have a shorter prefix, I can't have a longer substring. So 1 plus LCS of I minus H, comma j minus 1 has to be less than or equal to 1 plus LCS of I minus 1 comma j minus 1, because this is allowing me to use a longer substring than this is. So optimal solution is less than or equal to our solution. All right. Happier this proof now? Apologize for the meandering pattern. All right, so then there's actually a fantastic visualization of longest common substring that I posted to the class webpage. It's amazing to me that the fastest way for me to find a particular web page isn't to do like wistl.edu/tilde+, but you type into Google, which is indexing billions of pages. That's faster than like going through. That's just like crazy. All right, so here is our recursion. So the x equals minus 1, like x and y here are the I and j, it's how far the string is going. And if the last two elements of the string are equal, you return 1 plus the previous one. And then this is beautiful. This is just we can do this as a recursive call, a table, or memorize. Let's do it as a recursive call first. We can do abracadabra and yabba dabba do. And we can run the recursive call. And can we pause this? I think we can pause this. We pause this, and so it's going through and it's saying the recursive call, if the last two letters aren't equal, it's 1 plus the longest common substring. But if they're not equal, then it's doing the first recursive call where it shrinks the first substring. So it's going back from the end and it shrinks as like, all right, what's the, and it's going to get down to this having no characters. And at that point, the recursion bottoms out because of this line, and it can make this go faster because it's really. All right, so what's the, so that, like, I love this recursive call tree. Recursion is amazing. Recursion is never efficient because you have to store, in this case, like 20 different sets of what your local variables and scope and that stuff from programming languages I don't know is. And also it highlights that this, like the recursive exponential algorithm is really slow, right? Because it's going through all of these subproblems. It's even gone through some of the same subproblems and subtrees multiple times here. So, okay, let's stop this. I'm not sure if I can stop it. Skip back, pause. Let's see if I can start the memoized version. Then I have to type it in again. Step back. That's going to take a really long time. All right, so the memoized version. The memoized version is doing the same thing. It's doing these recursive calls, but then it fills in this table as it's going. And there's something a little bit interesting about this memoized table. What I think is interesting about this memoized table is it has gaps in it. It has holes in it. So why does it have holes in it? Maybe we have a different one. Like, let's make this funny. Ha 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 ha. And let's make this evil. Mwah, ha, 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 ha. All right, so now we do the memoized version. It goes through and it has So this is actually really cool in the fact that this memoized version is super efficient. And the reason it's super efficient is our recursive structure is not that when I'm computing the I comma j element, I need to do the I minus 1 and the I minus 1 comma j minus 1 and the I comma j minus 1. It's an if statement. If my two strings match at the end, then I only need to do this recursive call. And so in this case, these strings match pretty carefully, and so we got a really long substring without having to explore the whole table. So we can also do this as the table, so you can imagine building up a table and saying, I want to compute the longest common substring for I comma j, and I'm going to start where I and j are 1 comma 1. So what's the longest common substring of the first character of each string? And what's the longest common substring of a 1-character prefix of and ya? And what's the longest common substring of y and ab? And then once I have those subproblems, I can do what's the longest common substring of ab and ya. And so you can build up the table from the beginning. So when you build up the table like that, there's different orders you could do it, but you end up filling in all the elements of the table. So it's kind of interesting that sometimes the memoized version, even though it's recursive and recursion has overhead, is much faster because it only ends up memoizing the recursive calls that are actually used. And in some problems, you use all the recursive calls. And in some problems, which recursive calls you use are data-driven. So in this case, which recursive calls you use are data-driven because if you have a match, you don't have to do all the recursive calls. So what's the scenario, the character scenario where you have to use all the recursive calls? This is if you have somebody who's laughing with somebody who's in pain. Oi, 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 oi. So then the recursive, oops, I don't have the recursive. Oh, no, stop. Ha 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 ha. Oi, 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 oi.
Oh.
Close enough. Right. So now even the memoized version has to match everything because it never gets to do this happy case where the recursion goes in both directions, or it goes in the diagonal direction. Okay, finally, this table and our algorithm, which is now nicely hidden. Is our algorithm really hidden? This table and the algorithm that are hidden just compute what is the length of the longest common subsequence. It doesn't actually tell you what that longest common subsequence is. So what would it take, what kind of decoration do you need to add to the algorithm to know what that longest common subsequence is? Here's the secret. In every dynamic program, when you do a max, all you need to store is which one is it. And that gives you the handle you need to end up walking this back. So if I start on this problem, here I would say, maybe we can make this shorter. Abra and Yab. So if we were to build our table from the bottom up, we would have Abra and Yab. And so our longest common subsequence here is of size 0. Our longest common subsequence here is of size 0 and size 0 and size, that's not very promising. Our longest common subsequence here is of size 1. And we can probably do 1 and 1 here. And then this one is, if these two are the same character, it's just, as I point to there, if they're different characters, it's the max of this and this. So they're different characters, so it's the max of this. So this is the one that's the max. I'm going to keep that arrow there. And then my answer is 1, because 1 is the max of this and this, but it's 1 because of this. And this is a special square where I actually found a match. So we're going to mark those as actual matches. And I keep doing this. AR, these are different. The longest common subsequence is the max of this and this. So it's a 1, and I go there. AA is a match. If AA is a match, I can say 1 and go up here. And I guess these all go back like this. All right, so let's keep going. I have B and B. That's a match. And so I can say it's 1 plus whatever's up there. So it's 2. I can mark this as a special square. This got marked as a special square. 2, this is a 2 here. B and R don't match, so I get a 2 here, but I had to go there to get there. This went there like this. Here, it's the max of these 2 because these letters don't match. So I put a 2 and I go here. And then the final row, I have B and a B. So I guess I could do 2 like this and go here. Or I could say cut this off and just go up there, but I might as well like use this character. And 2 and 2, oh, I get to choose a max. It's not clear which one I want to choose. I don't know how to choose. It's either one. The max would probably pick the first one of the 2, depending on how your language is. It wouldn't do something random. I would do something random. Let's just say it goes left, 2, and those don't match, so it's 2. So now when you go through and you say, what is my longest common subsequence? You go to a character, you say, you got a 2. How did you get a 2? I got it from here. How did you get this 2? I got it from here. Hey, this is a place where these 2 match. So the last character of my longest common substring is a B. How did I get here? I came from here. How did I get here? I came from here. That was a special character. So my previous character of my longest common substring was from there. So that's the walking back. And at the end of the table version of this, you can see, or the memoized version of this, you can see it walking back. Let's do ha 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 ha, wah ha 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 ha. And our table, so it's going through and building the table. Go a little slower. Oh God, that's painful. It's actually kind of a cool animation. And so now it's walking back, walking back, walking back, walking back, walking back. I guess this is like an exact copy of the string, so it's super easy at the end. Questions? All right, last chance for questions. That's all I've got for today. So as a congratulations for finishing homework 1, you can all leave a little bit early.
Alice doesn't look like this. Oh, it's just her like picture, which happens to